All right. How's everyone doing? Pretty good turnout. Last week before freedom, I'm better. That's fucking freedom. 1 week is freedom. You have to, in life, you have to enjoy any small good thing that you get, right? Because here's the thing, there's like rain is important, right? Bad times are necessary for you to appreciate the good. And similarly, too much good times, makes you unprepared for when it gets rough, right? Okay. I mean, we barely know what rain is in California, but so we're gonna take that 1 week. We're gonna like apply ourselves, or we're gonna completely check out. That's up to you. But the work's gonna get done, right? Or we're gonna there you go, fail. I don't want that second thing to be true. And so I decided that this is probably the best way to give feedback. Because I was experimenting with a couple other things and you guys couldn't see my comments. And then I tried to put it into the little box and it doesn't really fit in the box very well. So the reason that I like this idea is because these can be a conversation just between me and you about specific problems. And what we can do in here is that when I give you feedback, if it doesn't say good or great, you can say where, what. And in particular, if you turn on in CoCalc, it'll have line numbers. So if you say like box 6, line number 12, I feel like I'm getting stuck. I can just type that in, or you can screen grab that, throw it in like an image, and then I can edit your code from there. Because I can't push edits back to you, it's really annoying, right? Because then I can't like correct your work. But there are some people who I've seen, oh, it's just a comma missing. Or, you're just using square brackets here and you should be using curly. And so they can be small changes. So this way we can have conversations about the work that you have done and the work that you haven't done. So I know this is a bit late to have realized how to do this. It's been almost a year and a half since I taught this. So is that okay? Okay. Have you looked at your feedback? Okay. So all of you have feedback now. And almost consistently, everyone's a little behind. That's okay. That tends to happen sometimes. That's what I think spring break can be for, if that's what your vibe is. Here's where we're supposed to be today. We're supposed to be done with 5 and not get a new homework this week. Right? So that's like, oh, sick. No new homeworks. Love that for us. And then we'll get some new homeworks here. I may throw in a couple 9 problems just to get us acquainted, but I really would have liked to finish chapter 9. Now, the things that I like and the things that I get in life are not always the same. You get what you get and you don't get upset. So we may do this today, or depending on how people feel, we may end up just doing some of the like starting problems that you're having difficulty with. Because if everyone has their feedback in front of them and they look at all the problems that they're struggling on, then maybe that's the best use of one another's time. I think you could get through faster methods pretty quickly, but that'll also depend on how you feel. So let's talk quickly about the semester project. Here is what I want to talk about. Any questions before we jump into this? Okay. Yeah. It will be. This will be the final project. Selecting a topic, that is obviously not the right date. What is the end of this week? The 8th? No. 9th? 30th?
No, 29th.
Let's go. All right. Okay. So you're going to do 2 things. You're going to demonstrate your mastery of the class to whatever level it is. You will demonstrate your ability to think outside of the box and to investigate your own work. These are marketable skills. ChatGPT doing your code for you is not a marketable skill. Coding will not exist in 10 years. I told you that at the beginning of the semester. So when I constantly berate you for no comments, no comments, no comments, this is what I'm talking about. I do not care that the code runs. I care that you understand how the code runs, right? Because we're not, solving Nobel Prize winning problems here. Okay. What we're trying to do is we're trying to learn in this class. We're trying to understand this beast that is coding. And we're going to add on top of it the beast that is physics, one of which we have a little bit of an intuition for. And the other one, which I don't know, it's a bunch of rocks that makes light and numbers, right? Okay. So we're going to think about a topic. It says 1 week from today, but maybe I should have said Friday. This does not mean that you'll tell me that day what you're thinking of. That means that starting today, you'll start thinking about these. You'll reach out, you'll ask questions to help scope the problem. You could submit it through CoCalc, but I also will accept it on Slack or by email or whatever. I prefer them on CoCalc because then everything's together and I don't lose someone's proposal. So here are the types of things that we'll be seeing. So we've seen computational physics, we've seen mathematics, we'll see visualization. Any topic of these can be used. So this is Monday. So quantum mechanics, perfectly good topic. You want to simulate how an electron moves. You want to simulate how, whether or not a large atom will be bound or unbound, stuff like that. Classical orbits. So you want to simulate a rocket going to Mars or to another planet while all 3 planets are moving. Be something fun to do. Lagrangian dynamics. This would describe any sort of simple mechanics, such as springs, coupled systems of pendulums like we've seen before. This will include air resistance, like if you want to hit a golf ball really far and you want the golf ball to have different sizes or stickinesses. You've seen that a little bit. Molecular dynamics. This will be the interactions between molecules in a lattice. So we'll look at different examples of that. Solid state physics, that's similar to this. Sound distortion or diffusion, that would be examples of waves in an area. So how do waves break around an object? Recursive maps, this is where you're going to get fun stuff like your Mandelbrot set. So that's the trippy stuff that, you play on a 4-hour loop and you zoom in and you zoom in and you zoom in and you always get a different picture, right? Have you seen those before? This is the Mandelbrot set. Let's watch a video of it because it's fucking sick, bro. Hopefully there's no music here. Okay. So, stop. I don't want to renew. I'm literally trying to teach. Okay. So can you go away? Don't renew. Here's what we're going to look at. This is an XY plane, but it's a special XY plane because it's in the complex space. And what's happening here is that this is representing places that are 0 versus not 0, hence the colors in a complex space. And what happens is you keep mapping onto it and you fill out the entire area. And what we'll do is you see this shape, right? It's got fun little bulbs and little things coming off of it. We'll zoom in. We'll always be zooming into this region. And you'll notice that the shape both replicates. We'll notice similar structures show up over and over and over. And that hints at the underlying mathematics. This is an example of a fractal structure where as you look closer, you see the same thing over and over. These are some really beautiful parts called the seahorses. Like seahorses. So you'll see those again here as well, right? And all these colors represent the number. This is also an example of visualization. So if you want to do any of your examples with cool visualization, you get extra points for it being pretty, right? And as we zoom in some more, you're like, wow, how could this ever end up being the thing that we just saw originally? And there it is. You see it? So buried deep down in here, you see the original shape because this is self-similar. You say it makes you uncomfortable? Okay, that's fair. And now we're gonna keep going into that same region. You gotta admit this is beautiful, right? Okay. This is just one example of what is called a regression or a logistic map. There are other ones, and in fact, I think we'll even see one. We can talk about fractal dimensions. So for example, you're familiar with two-dimensional information, like the stuff that's on the board, right? How long is the California coastline? What? It's infinite. Why? Exactly, right? So what happens is if you just draw like 1 and then 2, right, you get like a number. But as soon as you start cutting it up more and you go into every bay and gully and maybe you're using a yardstick, you'll get a much larger number because the coastline is moving, right? Okay, and then if you use an even smaller number, like let's say you start to measure the width between individual molecules, right? Now it has all this curvature that you've never even seen before. So there's an idea between the idea of dimensions, that you have something that's one-dimensional, which would be like a line, two-dimensional, which would be like in this region, and you can have stuff in between 1 and 2 dimensions. And only in a place like a computer can you represent that really easily, the transition between a two-dimensional to say a 2.5-dimensional shape, right? So if that's interesting to you, we could do that. Fluid dynamics, you can boil water. That's one of my favorite things to do. And I'm not talking about like making, tea or ramen. I'm talking about on your computer, boiling water. You could talk about diffusion. So you want to talk about maybe like the heating of the surface and seeing how that goes into the ground below, how that affects air, how that affects the surface. Talk about stellar structure. It's not very difficult to describe how the temperature and pressure functions as you go out in radius, and you can model that on a computer fairly straightforwardly. If you care about cryptography, I've had students do like how you crack ciphers and how you create ciphers so you can send secret messages to your friends. It's fun stuff. So anything that is roughly physicsy and uses a computer. It can be mathy and uses a computer, but the main requirement here is that it uses a computer. If it's something that can be done analytically, it's not applicable. Okay, so you can use an analytic technique, right? If you can differentiate something and then like check your answer when it's the easy version and then you make it harder, I always like that. So what I mean by that is, let's say you start with an equation and you want to test whatever you're doing. So you start with some equation, you test it for the simple case, you get what you expected from the analytic solution. Good, right answer. And now you change that equation so that it's more complicated. And then you can't do it by hand anymore. You can't do it analytically, but now you can trust your computer a little bit based on that previous input. Does that make sense? So we've already seen certain examples of this, right? We saw an example of charge distribution in a box, and we're going to see more examples of that soon. We will see examples of heat diffusion. We will see examples of particles like electrons in a potential well. But you might also ask yourself, what about a electron, say, in a hydrogen atom? You could create that as well. Does that make sense? Okay. So if anything sounds interesting to you, you send me a message and be like, I'm interested in XYZ. And I'll tell you, yeah, that's a great idea. Let's think about this problem. Let's work on it a little bit more. That makes sense? Okay. It should be about the length of 1.5 homeworks on a single topic. It will have comments. And it will describe what you did and why. This second part is really important. I see some people who are putting in comments, and I'm really happy about that. But then they get to the very end, and they say nothing. And it's actually more important to me that at the very end of your homework, you demonstrate why you knew that answer was correct. Did you learn anything? Or did you just exist, right? One is great. Just existing is good. But it's not as good as explaining what you did, right? Okay. You'll see some techniques that we haven't encountered yet. These include solutions for linear and nonlinear equations. So this is like algebra. And in week 14, 15, you'll see random processes and Fourier transforms. Random processes in particular are really cool. Like you can simulate random walks. So what would a molecule do in like if you dropped, say, a piece of pollen into water, you can watch it move around on the screen. It's called Brownian motion. It's how we discovered that atoms are individual things and not a glob. And you can simulate that with a computer as long as you know how to do random things on a computer. So let me know if you want to do any of those, and we can incorporate those in your project. You're allowed to work in non-CoCalc environment. If you have Jupyter on your own machine, you can make your own Jupyter program and work on it whenever you want, and then just send me the final version. Hopefully we're checking in and you're running into problems. You're sending me a version of your code. I fix it. I send it back to you. That would be great. Here's how you're going to get points. Okay, you have a presentation. I don't care what if it's PPT, PDF, I don't matter. But we're not going to be reading your code. You will not pull up your CoCalc and slide down from one to the other. That's not what we're doing. It's slides. So you'll choose one slide for why you chose the project. This will have words and pictures on it, not your code. You'll have one slide for why other people should give a shit, right? What's the motivation, why you want to hook them in? If you ever wanted to hit a golf ball further, just do X, Y, Z, right? We had 2 people do golf balls last year, or the last time that I did this. 3 slides for the project and main results. So this can include your technique. You can say I did RK4, but I don't need to see your RK4. Unless it's something very specific where you said, hey, I did this really cool thing that I think people should know about. If you're proud of a very specific piece of the code, I'll permit a small snippet, right? Okay. Then you have a summary and any backups. So it's pretty quick, right? 7 minutes. A couple minutes of question and answer. You'll get points for asking questions of other people. So as you, the audience, sit there, I will be keeping track of who's asking questions. Okay. Okay. Is it cheating or citing? You should not expect to write every program from scratch, but copy and paste is also unacceptable without citation, right? So if you need help, that's great. Work in groups, I don't care, right? It's a long project. It's the whole semester. You can find code online almost everywhere. If you adapt it, let me know. Hey, I grabbed this. I'm using it for this technique for this reason. I added these comments. I know how this works, right? Okay. Here's the final project rubric. Does it contain an algorithm that solves the problem? Does your code run? Does it give the correct answer? How do you know it's the correct answer? This one will be really important because you're solving a problem here that no one has the answer to because it's your problem because you created it, right? And in fact, this is a marketable skill because usually the answers can't be found online. Real jobs in the real world, right? There's no answer online for how much money was used in this sector or how many energy units were used over here. You have to find out and you have to learn how to either trust or not trust that result. Right? And similarly, does it have comments and shit? Okay. Note that using work that's not your own without citation is an automatic. Okay. Questions? Here's the rubric for the presentation itself. Does it address the material? They demonstrate a mastery of your chosen topic. Do they relate the material to the class? And then if you ask other people questions. Questions, comments, concerns? Okay, that'll be posted to Canvas later today. Okay, so now we're at a crossroads. What do we want to do right now? So I've looked at a lot of your feedback. Some of you do really well, some of you less than well. That's okay. But as the semester goes on, material just keeps piling up and you just have more to do. Like, well, I already know that I'm not doing well in that class, so I might as well not do that class. And that's just an F, right? So let me know. Close your eyes. Close your eyes. I see a lot of eyes. Close your eyes. Okay, close your eyes. Raise your hand if you would rather work on homework right now. Okay, put your hands down. Open your eyes. Okay, we're gonna work on homework. Okay. Here's what I would recommend. Start, where did it go? Oh, there it is. Okay. So open this up. Right? And in particular, if you start at the very beginning, some folks have already done, all of the first problem. Some people haven't. So what I'll do is I'll go around. I won't do any of the problems, but we can talk about how to start them. And in particular, thinking about them just like pair programming problems, right? We can talk through, okay, people are going to make this common mistake. So almost everyone on 3.3 just plotted it once and then left it. And I gave almost everyone the same feedback, which is try experimenting with the colors, try experimenting with, it's your opportunity to sort of play with visualization, right? Okay. And almost, I would say like 80% of people need more comments. Okay. So that will push the schedule a little bit, but fuck it. Yeah, we'll just not do interpolation. I'll move these over later. Yeah, I'll move these over later. Interpolation is not that important. We'll learn that in another class. I promise.